As part of my problem series in this video, I will be analyzing a two-loop circuit with multiple resistors and two power supplies. Once I am finished with this series of problems, I'll be posting them in my stand store at this web address. Before proceeding, I want to explain the three web addresses that you will be directed to using. You have already seen the first here. This is a web address of my stand store, which will give you direct access to all of my electrical courses. On the last page, you'll find an address that will direct you to obtaining the 50-page crib sheet and notes that will not only be handy when you're taking my courses in my stand store, but also for reference during any time during your career. Here you'll also be asked for your email address, which will not be shared with anybody or distributed in any way, but it will allow me to keep in touch with you and let you know of any additions or updates to my courses and or blogs. Near the end of the video, I'll be introducing you to a supplier of electrical products, which in my estimation are of value worth paying attention to. Let's look at another example of a mesh equation and go through the steps required to solve it using mesh or loop current analysis. Step 1 is to draw the loop currents. Loop currents I1 and I2 are drawn in a clockwise direction in each window. The loop currents or mesh currents are fictitious currents that enable us to obtain an actual branch current more easily. The number of loop currents required always equals the number of windows in the network. This assures that the resulting equations are all independent loops and may be drawn in any direction, but assigning a clockwise direction to all of them simplifies the process of writing the equations. It leads to less confusion, and similar to the previous solutions that we looked at, if loop currents turn out to be negative, then the assumed direction of the current is opposite to that of our original assumption. In step 2, we indicate the polarities of each voltage drop within each loop. Identify the polarities to agree with the assumed direction of the loop currents. Starting with loop number 1 at R2, then R3, and ending with E1. Notice that the voltage drop across the resistors are positive with respect to the current flow, and the voltage drop across the power supply is negative because it is not dropping the voltage in the direction of the current, but doing just the opposite, providing a voltage rise. Writing Kirchhoff's voltage law around each mesh in any direction, it is convenient to follow the same direction as the loop current. Therefore, loop number 2, we notice that the polarities across R3 are the opposite for each loop, and the polarities E1 and E2 are unaffected by the direction of the loop currents passing through them. Also, with the assumed current flow of I2, E2 provides a voltage drop and therefore considered positive in the loop equation. In step number 3, we write Kirchhoff's voltage law around each mesh following the same direction as the loop current. For the I1 loop, we get -8 plus 2 times I1 plus 4 times the quantity I1 minus I2, all equal to 0. And for the I2 loop, we get plus 24 plus 4 times the quantity I2 minus I1 plus I2 equals 0. We can now use these two equations to solve for I1 and I2. Let's rewrite these two equations, removing the brackets. We can now collect the like terms and end up with these two equations. The first equation can be simplified by dividing both the left-hand side and the right-hand side by a factor of 2, and rewriting both equations gives us these two equations. We would now like to reduce the two equations to one equation with one unknown. Let's first solve for I1 by multiplying the first equation by 5, and this gives us 15I1 minus 10I2 equal to 20. And the second equation we'll multiply by 2, which gives us 8I1 minus 10I2 equal 48. We can now reduce the two equations to one with one unknown by subtracting the second from the first. This removes I2 and leaves us with the equation 7I1 equal to minus 28, and allows us to solve for I1. I1 is equal to minus 4. We now solve for I2 by using this equation. 3I1 minus 2I2 is equal to 4. And replacing I1 with minus 4 to give us this equation, which simplifies to minus 2I2 equals 16 and allows us to solve for I2, which is equal to minus 8 amps. The minus sign for I1 and I2 indicates that the two loop currents flow in the opposite directions to that which we assumed in the first place. They both flow counterclockwise. Loop current I1 is therefore 4 amps in the counterclockwise direction, and loop current I2 is 8 amps, also in the counterclockwise direction. This true direction for loop currents I2 through resistor R3 is from C to A. The true direction of loop current I2 through resistor R3 is from A to C. Therefore, in reality, the current through R3 is I2 minus I1, or 8 minus 4, which is equal to 4 amps in the direction of CA. I want to introduce you to another product that's out there that is worthy of paying attention to. The 𝐃𝐈𝐒𝐂𝐋𝐀 solar generators are available in various capacities. Depending on the running and starting watts required, you can choose the right size of solar generator. For example, you can choose a small solar generator if you want to run laptops or cell phones, or perhaps a small freezer. On the other hand, a large solar generator would be ideal for extended power outages. To find out more about these battery generators and to keep up to date on any sales or discounts that are available, simply go to this web address. And remember, this video has been brought to you by PSPT, where you will find electrical training videos when you go to this web address, which will also give you a free copy of my 50-page crib sheets that you can use while viewing any of my courses, or just keep it handy during your everyday work.